We're diving into the locally linear embedding (LLE) algorithm, a technique used to reduce the dimensionality of data. Think of it like simplifying a complex map into a simpler one while trying to preserve the important relationships between different locations. We'll focus on one of LLE's key parameters, n_neighbors. This is a multiple-choice quiz about understanding how the n_neighbors parameter in the LLE algorithm affects the results. Get ready to test your knowledge. I'll guide you through each statement and help you understand how n_neighbors influences the final result. Think of n_neighbors as the number of nearby data points considered when LLE tries to figure out their relationship. Increasing n_neighbors means that you consider more neighboring points when calculating the relationships between data points, creating a smoother, more consistent result. I imagine it like connecting more dots to form a smoother line on the simplified map. This statement is wrong. Decreasing n_neighbors actually reduces the computation because we're considering fewer points for each calculation, not increasing it. If you only consider one or two neighbors, you risk creating a very fragmented and disconnected map, because the overall relationships aren't considered sufficiently. This statement is incorrect. Finding the best n_neighbors value is a delicate balance, affected by both the true dimensionality of the data and the presence of any noise or errors in the data. It's like choosing the right level of detail on a map. Too much detail and it's cluttered, too little and it's inaccurate. This question asks you to identify correct statements about the n_neighbors parameter in the locally linear embedding (LLE) algorithm. Let's break down each option. I find that a small number of neighbors for each data point in LLE can lead to a fragmented embedding. Imagine trying to reconstruct a puzzle with only one or two pieces at a time. You'd likely have many small, unconnected clusters. That's similar to what happens here. The limited local information makes it difficult to connect points globally. I see that this statement is incorrect. Decreasing the number of neighbors actually reduces the computational cost, as fewer distance calculations are needed to find the nearest neighbors. The opposite is true. Increasing neighbors increase computation cost. I see that this statement is also false. Finding the best n_neighbors value is like finding the Goldilocks spot. It depends on both the data's inherent structure, its dimensionality, and the level of noise in your data. Too few neighbors might not capture the overall shape of the data, while too many might be overly sensitive to noise. It's a balance. I think that when you increase the number of neighbors, you're considering a wider area around each point when reconstructing it. This helps create a smoother embedding because you account for more of the data's overall structure. It's like smoothing out wrinkles on a fabric. I'm analyzing a question about the locally linear embedding (LLE) algorithm in sklearn. We're focusing on how changing the n_neighbors parameter affects the results. LLE is a dimensionality reduction technique. Think of it like trying to flatten a crumpled piece of paper. You're trying to represent a high-dimensional dataset in a lower dimension while preserving the important relationships between data points. The n_neighbors parameter controls how many nearby points LLE considers when doing this flattening. This is a multiple-choice question. We need to analyze 4 statements about the effect of the n_neighbors parameter in LLE and choose the correct ones. The parameter, n_neighbors, dictates the number of nearest neighbors to consider during local linear reconstruction in the LLE algorithm. This statement says that if you increase the number of neighbors that LLE considers, you'll get a smoother, more consistent representation of your data in lower dimensions. I agree with this because a larger neighborhood averages out more local variations, resulting in a smoother output. If you use only one or two neighbors, LLE is basically only looking at tiny local areas of your data. This means it might miss the bigger picture and create a very fragmented or disjointed output which may not reflect the global structure of the data. This statement is incorrect. I found that decreasing the number of neighbors actually reduces the computation needed because LLE has to calculate fewer distances between points. This is false. The best number of neighbors depends on both the inherent dimensionality of the data and the amount of noise. A noisy dataset might need a larger number of neighbors to smooth things out, while a low-dimensional dataset might work better with fewer neighbors. I'm focusing on the _n_neighbors parameter in the locally linear embedding (LLE) algorithm. LLE is a dimensionality reduction technique. It tries to represent each data point as a combination of its nearby neighbors. The _n_neighbors parameter controls how many of these neighbors we consider. This question tests your understanding of how changing the number of neighbors affects the results of the LLE algorithm. Let's look at each statement carefully to see how it works. I've found that increasing _n_neighbors makes the embedding smoother because you're considering a wider range of data points when you create the embedding. It's like connecting more dots when you draw a picture, it gets smoother. This statement is true. If you only consider one or two neighbors, the embedding can become fragmented because you're only looking at very local information. The overall structure of the data could be missed, so the resulting picture becomes broken up. This statement is true. This statement is false. The opposite is true. Decreasing _n_neighbors actually reduces computational cost because I'm doing fewer calculations. I'm looking at fewer neighbors to make the embedding. It's like drawing a picture with fewer dots. This is false. The optimal value depends on both the inherent dimensionality of the data and the amount of noise present. Noise can distort relationships, and a good choice of _n_neighbors will help smooth that out. It is important to experiment to get the right balance for your data. This question focuses on the impact of the _neighbors parameter, which controls how many nearby data points LLE uses to reconstruct each data point. I'll examine each statement to determine its truthfulness. It tests my understanding of LLE, a dimensionality reduction technique. This is false. I found that the opposite is true. Decreasing _neighbors actually reduces the computational cost because fewer distance calculations are needed. LLE needs to calculate distances between a data point and its neighbors. Fewer neighbors mean fewer calculations. This statement is correct. I agree. If I use only one or two neighbors, each data point's reconstruction relies on very limited information, potentially leading to isolated clusters and a fragmented final result. Think of it like trying to build a house with only a couple of bricks nearby. You won't get a very solid structure. This is incorrect. I disagree with this statement. The best value for _neighbors depends on both the data's intrinsic dimensionality, how many dimensions it truly has, and the noise level. A noisy dataset might benefit from a larger _neighbors to average out the noise. A low-dimensional dataset might work better with a smaller value. It's always a trade-off. This is true. Absolutely. Increasing _neighbors allows LLE to consider a broader context for each point, leading to a smoother, more globally consistent representation. Imagine it like using a larger paintbrush. It smooths out the strokes. It helps capture the bigger picture of the data. This refers to a parameter in the locally linear embedding (LLE) algorithm, a dimensionality reduction technique. It controls how many nearby data points the algorithm considers when modeling the relationships between them. Think of it like this. When you're trying to understand a person's behavior, you might look at their closest friends. The parameter, n_neighbors, determines how many friends you consider. This is the core question of the quiz. We're asked to evaluate statements about how changing the number of neighbors affects the outcome of the LLE algorithm. I agree with this. If you consider more neighbors, friends, when constructing the local relationships, you'll get a smoother picture. It's akin to smoothing a curve by using more data points to define it. The final embedding, therefore, will reflect more of the global characteristics of the dataset. I also agree with this. If you consider too few neighbors, you'll get a disjointed, fragmented embedding because the reconstruction is based on limited information, much like only looking at one or two people to understand the characteristics of an entire group. I disagree with this. Actually, decreasing the number of neighbors will reduce the computational cost of the algorithm, because fewer computations and comparisons are needed. Conversely, increasing it does increase the computational cost. I disagree here too. The optimal value depends on both the intrinsic dimensionality, the underlying structure of your data, and the noise level. More noise might mean you need a larger value of _n_neighbors to smooth things out, but too many neighbors can blur the detail. The best choice is always a compromise. A bit of experimentation is required.